Right, so looking at number 4 from the 1998 ACS test, it asks, which species is most likely to undergo a 1,2 hydride shift? So we should be thinking, why would something undergo a hydride shift? What kind of carbocation would it be? What kind of carbocations would undergo a hydride shift? Primary or secondary. Right, so we should write. Right, I would write a note to myself, right? I'm going to give you scratch paper. Say, hydride shifts not likely what? Tertiary. Right, unless we go tertiary benzylic, right? So we look at our molecules and we say, well, A already has, right? It's a benzylic carbocation. That's really stable. That's pretty good. We look at C. C is a tertiary. That's secondary benzylic. C is tertiary benzylic. D is secondary, and B is secondary. So we should at least have narrowed it down between which two things? B and D, I hope, right? So let's draw B and D. So a lot of these questions in this test are going to have to do with benzylic positions and resonance. It's going to be a big theme, right? So if I'm drawing out B, and I draw out D, here's the thing. They both will undergo a rearrangement. But don't forget, what kind of rearrangement are we interested in this case? Hydride, which means we're moving what? An H. These are both secondaries. This is going to undergo a rearrangement, but not with a hydride. What's it going to move? That's a methyl. Methyl shift. Right? So be careful. So D will definitely undergo a shift. It just won't be a hydride shift. Right? Now B though, right? B, there is that H there. And that'll be that H shift. Right? So a couple things. They wanted you to recognize, do you understand carbocation stability? Do you understand the benzylic position? And do you know what a hydride actually means? It means moving an H, not a methyl. Right? So kind of think about those things they're asking you. So the answer, of course, then is B. B is the answer. Good. Number 10 is asking us, the melting range of 4-nitrobenzyl alcohol is reported as 92-94, and the melting range of triphenylmethane is 92-94. Which statement most accurately reflects the expected result for the melting range of 50-50 mixture of the two? So what happens, right, if I have squares and circles, right? So they both have the same melting point, 92 to 94, right? But now I'm going to take both of these guys and mix them, right? Well, they're different. They're two different molecules. They're different molecules. I don't know who's a square, who's a circle, but I know they're different, right? They're not the same thing. They just happen to have the same melting point, right? So what's going to happen, right? If I mix them together, what's going to happen to the melting points? They're going to go down, right? So what are our answers? The melting point will have the same. That's A. It'll melt over a broad below. It'll have a sharp melting point below, or a sharp melting point above. What's going to happen, do you think? Is it going to be a sharp thing or a broad thing? What can you eliminate right away? You should be able to eliminate C. You can eliminate A and C, right? You can eliminate A and C right away, right? And then the question is it going to be sharp or broad? So broad kind of means, right, that it's not going to be that, right? They're like Legos and Lincoln Logs. They're not going to stack up very well. And the melting point is going to be broad because it's all messed up, right? So it's going to be a range. So it should be nice and broad. It won't be sharp, right? Sharp melting points have to do with pure substances, right? Something that's pure would be like really precise. So a broad and below, right? Because things wouldn't stack up very well, those intermolecular forces. So what's the answer for this one? I think it is B, right? It's going to be broad and lower. So broad and lower. So let's look at number 66. And it says, what is the product of this reaction? So let's draw this out. We almost did one exactly like this at some point. And we're saying there's H plus, or that's H3O plus, same difference. And then 2 is baking soda, bicarb. All right. So if you look at this, what kind of functional group do we have here? An imine. And who remembers what imines come from? Primary amines. And in this case, what else? A ketone or an aldehyde? A ketone. So primary amines and ketone. Let's look at the answers. Primary amine and a ketone. So I look at A, there's a primary amine, but there's no ketone. I look at B, primary amine, no ketone. C, primary amine and ketone. D, aldehyde and primary amine. Now, why did I know it was a ketone? If you looked right here, right, this carbon was where the C double bond O was, right? And if you look, this is a carbon and that's a carbon, so you had to know there, right? If you broke an imine in half, right, there is where it would be. There would be a ketone, right? So the product of this which is C. But look, you didn't even need to know how to do the mechanism. If you knew what we talked about, I've told you what an imine comes from, a primary amine and a ketone or aldehyde. And you looked here and you said, well, it has to be a primary amine. In this case, it has to be a ketone because these aren't H's. And they even made it easier for you. Look at the thing and it says, well, only one of them has a ketone. It has to be C. 68 is asking us which ion is not aromatic. But really what it's asking us, do you know what aromatic means? That's what the question really is here. So what's the definition for aromatic? An aromatic compound is what?
Double bond, there's an open P orbital.
Nope, that's not the definition of aromatic. You have to have an uninterrupted pi system in a ring. Uninterrupted, spelling's horrible. Pi system ring. That's an uninterrupted. I'm saying it out loud too, right? So that means non-stop. Pi, I'm going to start saying that from now on. A non-stop pi system. Fast 7. Non-stop pi system. In a ring, has to be in a ring, of course. And then something about the electrons. You have to have an odd number of pairs of pi electrons. Those are the two qualifiers. So it's got to be a ring, and it's got to have an odd number of pairs. So let's look at the answer. Let's look at the answers. Are they all rings? Yeah. Yep. So well, that doesn't help. Well, they're all rings, and are they all uninterrupted pi systems? Is everything sp2 or sp3 hybridized or sp hybridized? Yep, they're all sp2 or sp hybridized, right? They all have p orbitals, so we can check that off. And now we got to look for the odd numbers of pairs. Right? Odd numbers of pairs. So let's look at A. A has, how many pairs of electrons does A have? 2. 2's not odd. Right? And everybody else, you look at them, even though they look weird, we know our definition. Just because something looks weird.
I thought open orbital was counted as one.
Of electrons. How many actually, are there any electrons? You just said it. In an open orbital, are there any electrons? So how would you count? It counts as part of the uninterrupted system, but not count as actual electrons, right? It's because it's open. And this one looks even weirder, but okay. All right, I can count. So 1, that's odd. 1 is odd. 1, 2, 3. 3 is odd. 1, 2, 3, 4, 5. 5 is odd. So the answer is A.
If number 3 had a negative charge instead of a positive,
That would be anti-aromatic.
Right.
It wouldn't be non-aromatic, it'd be anti-aromatic.
An anti-aromatic is when it,
Even anti-aromatic, so actually the number 2 is, I mean, the definition of non and anti-aromatic are kind of the same thing, right? I would call number 2 anti-aromatic, but see the question says not aromatic. It doesn't say is anti or is, right? It says not aromatic, right? So anti-aromatic things have even numbers of pairs in an uninterrupted pi system, right? But lots of things are non-aromatic, right? Right, like ethanol is non-aromatic. That doesn't mean it's anti-aromatic. Anti-aromatic means like a bad thing almost, it's higher in energy. Make sense?
yes.
Good. At number 20. So, this one's asking for an optically activated saturated ketone, C7H14O. It reacts with a catalytic amount of KOD in CH3OD to give a ketone C7H9D5O. Sorry, D5O. So what you need to think about here is all of a sudden we had 5 deuteriums go on. How would that happen? So let's think about, we have a ketone and we're adding in OD minus, and we're doing that in deuterated methanol. So what's OD minus? What is that? It's a base, right? It's like KOH, right? It's a base. What do bases do to ketones? We've just been talking about this. What do bases do to ketones? What do they do? If OD minus is a base, the ketone is going to have to be what? Oh, come on, guys. Can ketones be acids? Right? If OD minus is a base, the ketone has to be an acid. Where are ketones and aldehydes acidic? The alpha CH. Yes? So what's going to happen here is we're going to deprotonate and change out these H's for deuteriums. So for every alpha H we have, we're going to turn it into a D. Because we're going to deprotonate, and then it's going to react with the solvent, which has a lot of D's, right? And it's just going to essentially switch out all the H's for deuteriums. Does that make sense to everybody? Right, what's going to happen is you're going to have something where you're going to make all these enolates, and they're all going to say, hey, solvent, I want that D. And they're going to keep doing it until all of the H's, all the alpha CH's have become D's. Because there's so many deuterated methanols. So we're going to exchange 5 of them. So now let's look at the answers. So how many alpha CH's should we be looking for? 5. So let's look at the answers. How many of them have 5 alpha CH's? Does A have 5 alpha CH's? Yes. A has 5 alpha CH's. Does B? How many does B have? 4. Does C have 5 alpha CH's? Okay. And what about D? Does D? How many does D have? So we're down to what 2 answers? At this point, you've just increased your odds from 25% to 50%. But we can keep going. So I'm going to shrink this. And I'm going to draw out A. And I'm going to draw out, what did I say? We said C?
Yeah.
That's A. C. And remind you, I'll give you scratch paper. You will want to use it. All right? Okay. So the second part says, to give a ketone that is optically active. What does optically active mean? It has an asymmetric center. Remember we talked about that? Asymmetric centers. So which of these has an asymmetric center? C does. Right? Right there. There's an asymmetric center. So the answer is C. Right? So it's a double layered thing, right? So you could have approached this a couple different ways. You could have looked at those ketones and said, well, which one has a stereocenter? Right? If you looked at ones right away and say which one of these has a stereocenter, you would have, well, A doesn't, but B does, C does, and D does. So you'd have 3 options there. Then you'd have to look at how many alpha CHs could be replaced. Right? But either way, there's 2 parameters. Do you understand that alpha CHs are acidic and can be replaced with deuterium? And do you know what optically active means? Right, those are 2 things they're asking you. Make sense? Questions?
I guess I'm not getting the difference between C and D.
C and D?
Yeah.
D doesn't have 5 alpha CHs that can be replaced. They told you that you get they told you get C7H9D5. So that was the other key. Yep. So 2 parameters: alpha CHs,
Yep.
all replaced with deuterium, and the optically active, right? Stereocenter.
Perfect.
So number 50. They will have retrosynthetic problems, but I promise you they will not be harder than mine. Yeah. So we have an epoxide. What do epoxides come from? You know how to make epoxides. Where do they come from? There's 2 ways to make an epoxide. Alkenes or from that BROH, right? Most of the time, alkenes are the way to go. Epoxides come from alkenes. All right, so let's work backwards and we'll say, I'm assuming that epoxide came from that alkene, right? Also, you should notice when you first analyze this, how many carbons does this starting material have? How many carbons are in the product? 7. So we have to add a carbon at some point. So we have an alkene here with an extra carbon. Do you guys know how to make an alkene with it? How do you make an alkene to add carbons? Who knows how to do that? Not Wenzel, but to make an alkene. I'm making an alkene. How do I make an alkene? Not Wenzel, but the Wittig. This is exactly the example in the Wittig we use, right? This can come from a Wittig, right? Wittig adds carbons, and it adds carbons in the form of alkenes. Wittig. Wittig. There's other ways to do this, but
Okay. Just
we'll speak in our own constraints. So that would have came from a ketone, right? And can a ketone come from an alcohol? Yes, it can. So now, if I look at this, right, so the other thing to think about, why did I think Wittig right away? Right, so when you first went 1 step back here, you knew it had to come from epoxides come from alkenes. But let's look at this particular alkene. Is that a Zaitsev alkene or a non-Zaitsev alkene? Non-Zaitsev. How do you get, what's the point of a Wittig reaction? One of the points of the Wittig reagent is that you can make non-Zaitsev alkenes, right? That was the whole point, that you can make alkenes that aren't, right, more substituted. The Wittig helps you do that. So that made me think Wittig. That's why I thought it here right away, instead of doing some sort of an elimination process, right, adding things. Because this was a less substituted alkene that you would expect, I thought Wittig right away, and that's why. We've convinced ourselves that Wittig should be going on here. That means we have that phosphorus reagent at some point. So if we look at these, right, I said Wittig. And if you know something about Wittig, you know it has something to do with phosphorus, question mark? Okay, so at this point, oh God, I don't know. Let's look at now let's look at the answers. So A, does A have phosphorus at all in it? Does B?
yes.
B does. Does C? Does D? Heck, I don't need to know anymore. It has to be B.
CRO3 I thought would make that into a.
That's it. Just on the basis of Wittig. So we'll go through it, but it has to be B. Because to make this non-Zaitsev alkene, I have to use a Wittig. Right? And plus it's a way to add a carbon too.
Didn't you say that there are many other
There are other ways to do it, but not to add a carbon. Right? So that was the other part of this was I went from 6 carbons to 7 carbons. Right? I can do non-Zaitsev alkenes, but not in the way that I would add a carbon at the same time. Wittig does non-Zaitsev and adds a carbon. Right? I needed to add an extra carbon here. So that's why I immediately thought Wittig. Right? You can do non-Zaitsev eliminations, but not at the same time add a carbon. So that's the trick here. So right, both essentially A and B both have right oxidation. So you could look at all of them and say, well, I know I probably need to go through a ketone at some point. Right? So some sort of oxidation process here. So A through C does that. So you can eliminate D that way. And then RCO3, right? This RCO3, this is equal to MCPBA. That makes epoxides. So that's the last thing you need to do is make the epoxide. So the other way to look at it is if you recognize this reagent, RCO3, that's the last thing you do is make the epoxide because that's the final product. That RCO3 should be the last reagent you use, and that's also in B. So let's convince ourselves B is right by proving that the other ones are wrong. So let's look at, so I've convinced ourselves B is correct. But let's look at why, in particular, something like D is wrong. So D, if I had those reagents, I would have an alcohol, H plus in heat. That's going to give me an elimination. There's a mechanism for that. You should know. But all right, there you go. And I'm going to add Br2 in water. That's going to give me a bromine and an OH, and they're of course going to be trans to each other because Br2 forms a bromonium ion. Water comes in and attacks. The other byproduct of this, of course, is HBr. And then the last step is the other way to make an epoxide, right? MCPBA takes an alkene and turns it into epoxide. But here we're going to take NaOH, Na plus, OH minus, and this will deprotonate this. Give us an O minus and a Br, which of course are trans to each other. This O minus can attack, and we will form an epoxide. The problem is we didn't add any carbon. We didn't form the right epoxide. That's why that Wittig is really key. Wittig forms an alkene, but it also adds a carbon at the same time. Good. Let's look at number 47. Now 47 has a carbon NMR, has a C13 NMR, right? C13 NMR. And now this might scare you right at the bat or make you nervous because you're saying, I don't know exactly what ppms, right, these things will be at. But what do you know about carbon NMR? For every peak represents what? A different type of carbon. So how many peaks do we have in our example here? We have 3 peaks, which means we have how many different types of carbon? So we have 3 types of C. Right, let me draw these out quick. So that's A, B, C, D, right? So a lot of people probably looked at this and said, "Oh God, I don't know carbon NMR." Right? I mean, right? Because it's hard to know those exact things. But all this was saying was, there's 3 peaks, so you need to have 3 types of hydrogens. Now you look at A. How many types of types of carbon? How many types of carbon does this have?
4.
This has 4. How many does B have?
4.
How many does C have?
3.
How many does D have?
2.
What's the answer?
3.
There it is.
What?
Right?
Why does D have 2?
Because these are symmetrical, right? This carbon's different, but these 3 are all the same.
Yep. Okay.
So all the question was really asking you was, can you differentiate the numbers of carbons, the types of carbons. You didn't know anything about, all you need to know about carbon NMR was that it represented, each peak represents a different type of carbon. You didn't need to know the ppms at all here. If you look at number 46, right, they're saying which reagent will accomplish this conversion, right? Now this is tough, because this is like saying either you know this or you don't,
Yeah.
right? It's kind of a one you know or not. But you can still probably maybe rationalize through it a little bit,
It's not osmium tetroxide.
right? So let's look at it. So we're taking an alcohol, a primary alcohol, and we're turning it into an aldehyde. So one thing to think about is this is going to be tough, right? Because usually we take a primary alcohol and we can turn it into a carboxylic acid, right? It's hard to stop oxidations, right? We want to take both of these H's. And the way I would tell you to think about this right, osmium, we know it does something else, hopefully. Has nothing to do with this. It does something else. It does that it makes a cis diol. So maybe we can eliminate A because it does something else. Now B is KMNO4. Not real sure about that one, maybe.
It's an oxidizing agent.
We know it's an oxidizing agent. We know it's an oxidizing agent. We don't maybe know exactly what it does. And then C is Na2Cr2O7 H2SO4.
The thing different between B and C is that there's acid.
And then D is PCC, it says. So at this point, maybe you're like, well, I know osmium does something different. I've never seen KMNO4. I've seen chromium, and I've seen PCC.
I thought we've seen it.
You've seen KMNO4. KMNO4 does oxidations, but it's pretty strong oxidizer,
Oh.
right? But you might not have known that. But then you say, well, I have two things I know, one thing I've never seen. I know Wenzel said when I see chromium, that's going to be big time oxidation, and they call this one PCC. I'm going to guess D, and D is the right answer. PCC PCC takes one alpha CH, just like bleach does, right? That's one of the ones we learned. We learned PCC, right? PCC takes one alpha CH from the alcohol, right, and gives you aldehydes, right? We've learned that, right? Remember that? PCC? We're going to look at number 40. It's asking us, it says, when allowed to react with HCl, which alkene will give an alkyl chloride in which the carbon skeleton has changed? So what does that mean when you hear carbon skeleton has changed? That should tell you something. What does that mean? Rearrange. There's going to be a rearrangement, right? Which one of these alkenes will rearrange? Right? So we should be looking for an alkene, right? Do we ever make primary carbocations? No. So we won't ever do that, but we should be looking for an alkene that will rearrange, right? Be careful. They said a carbon skeleton rearrangement. So remember that problem before was about a hydride shift? This would have to be, we have to look for a carbon skeletal rearrangement, meaning what kind of shift? It has to be a methyl shift. If it's not a methyl shift, that's not the kind of rearrangement they want. So if you look at the questions or the problems, that's A, B, C. Yep, they're not drawn out the way we'd like them. So you gotta get good at drawing them out. Yep, it's a tough one. And then D. All right. So A, B, C, and D. So if you look at A is weird. You put a plus charge here, a plus charge here. There's going to be no rearrangement. You'd get a tertiary or a secondary, and if anything, you'd have a hydride shift, right?
Yeah.
B, if you put a plus charge here, you'd have a rearrangement. What kind of rearrangement, though? It'd be this hydride would shift, right?
Yes.
That's not a carbon.
Same thing.
Here, this is secondary. You'd have a rearrangement, but it'd be this H that shifts. Here, you get a plus charge here,
Ooh,
right?
yeah.
It'd be one of these carbons. So it has to be D. Now look at what they're asking you though, right? Things that they're asking you. Two things, right? Carbon skeleton, meaning methyl shift, right? That could be tricky, but they mean methyl shift. Also, they're basically asking you, do you understand if you have HCl react with an alkene, how did you guys know to put the plus charge on this carbon? Why? Because that's a secondary, right? You never make primary carbocation. They're also asking you that. Do you realize you never make primary carbocations? That's the other part they're kind of asking you. Good.